Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today is my full name, the Liverpool group. Michael and I know each other through the robotics area. I'm student council, trying to get some interest around companies doing robotics, particularly in the education space. And other people interested in the group, space and robotics. This seems a great synergy with the client Michael today. Michael is going to talk about the space elevator, something that I only thought was science fiction until I saw these guys. It's time to do this for real. So we can present about the space elevator to see whether it's real or not. Michael, over to you. Thank
you. Before I get started here, let me get an idea of what you think you know about the space elevator. What have you heard about so far? What have you heard recently? Any preconceptions? Yeah.
I think from Mars estimated at $100 billion.
Okay, right. It's going to cost less than that. That's good. Any other? All right. What's that?
Arthur C. Clarke wrote about it.
Right. That's really one of the most common.
Can you repeat?
Arthur C. Clarke wrote about it. The space elevator has been around. The idea of it has been around for about 100 years. A Russian researcher, Tsiolkovsky, I have a hard time pronouncing that, went out and he was looking at the Eiffel Tower and he thought, what if you could extend that? What if you could build further and further and further and further? And as long as you kept the balance between gravity and centrifugal acceleration, you would be able to climb back and forth with a rigid structure back and forth into space. Clearly 100 years ago, there was no way near the technology required to do that. So it sat on the shelf for a while. Another Russian came along, Gsŷtynov, who had some slightly different perspectives on how to do it. He didn't want to make a tower. He wanted to make a relatively flexible structure. Still wasn't possible. Arthur C. Clarke, the guy who wrote Space Odyssey 2001 and about 1 million other sci-fi books, he's been credited with some of the visionary work on satellites. One of the first satellites came from some of his original thinking. And it was, again, science fiction. He wrote a really great science fiction book on how to do it, and it was wrong in a lot of ways, but it pointed out that there was still some worthwhile thinking that was going on. Fast forward a couple of years ago, Dr. Smitherman, from working in NASA, I think he was at Marshall Flight Center at the time, did some work on this again, and he and Jeffrey Landis came up with a tall tower version, which was something like 50 kilometers high. Again, a rigid structure. No, am I wrong there?
Don't you have to go about 40,000 kilometers?
Right. But what his plan was to make a rigid structure 50 kilometers high and then attach the ribbon. Again, there was no material that could do that. Dr. Edwards came by about 4 years ago. He was doing some work at Los Alamos National Labs, and he really had some of the original breakthroughs, the things that said, if we take carbon nanotubes, and I'll explain about them in a couple minutes, if we take carbon nanotubes, we can maybe build this. Carbon nanotubes probably have the strength requirements that we need. There's still a whole bunch of other issues. We'll talk about some of them. But suddenly there was a breakthrough in the thought process that this might be possible. So that's a little bit about the history. It started out as science fiction. How many of you have read the Red Mars series by Kim Stanley Robinson? All right. I've had a couple of conversations with Stan, and he's actually apologized to me. But for the people that haven't read the book, Mars gets colonized, and they build a space elevator from Mars, and it gets attacked by terrorists. It gets brought down twice. Both times it happens, they used a huge cable array, It wrapped around the planet 3 times, caused molten death and destruction at the equator. And that's actually one of my #1 questions that I still field today because of that book. So he's apologized to me, but because it made really great reading and really bad science, but it's all right. How I want to work this morning is we're going to have a fairly long question-and-answer session towards the end, about a half hour or so, because there's usually a lot of questions. I never can answer all of them in the amount of time. It's a complicated project. I can only give you an overview. Bear with me for about the first 10 minutes or so as I bring people up to speed, so we're all talking about the same kind of space elevator. And then we'll start getting into some of the technical requirements, some of the problems, some of the challenges, some of our successes. We'll talk about some of the robotic developments that we're working on. We'll talk a little bit, don't want to bore you, about the business side of this. That's, by the way, my background. Oops, sorry. I am not an engineer, so I can parrot some of the answers back to you if you want from the engineers. I'm not a physicist. We have a whole raft of people like that working on the team. I'm the business development guy, so I can answer a pretty fair amount of technical questions, but there's certain limits. I know a fair amount about the robotics. I know a fair amount about the carbon nanotubes. Those are areas I'm putting a lot of attention into. I don't know anything about lasers. I know hardly anything about photovoltaics. So if your questions start going that direction, can't help you. All right. First off, the space elevator concept, the thing you have to keep in mind is balance. As long as you're balancing the forces of gravity and centripetal acceleration, if you have a ball and a string and you're waving it over your head, as long as you're balancing those two forces, that string in the middle will stay straight. If you expand that string to Earth-sized, and the Earth is spinning 1,024 miles an hour, you've got a lot of energy built up in that string. And that string will stay rigid, and if you grab the sides of it, you'll be able to climb back and forth. That's the basic premise of the space elevator. You'll be able to climb back and forth into space reliably, inexpensively, safely, commercially. And that's what we're talking about. So what I'm going to show you first is the construction scenario, how we intend to build this. What I'm going to show you is about 2 years old. We've got that's our baseline. That's what we're drawing all of our original conclusions from. We've modified it slightly. There's some technical details. If you want, I can get into them. Overall, 96% of this is correct. There's some details we're going to make some modifications to. So let's start here first. The screen will clear up in a second. Okay. What you can't see very well yet, but it'll come into more focus here in a second, is there's 4 major payloads. 2 spools of thread, a rocket motor, and solar energy panels. What we're going to do is we're going to take 4 rocket rides, conventional Atlas or Delta heavies. We're going to go up to low Earth orbit, about 300, 400, 500 miles up, and we are going to assemble these 4 payloads. I'm going to stop it here for a second. Always keeping in mind balance. There's a certain amount of cargo that we can launch into low Earth orbit. We could do a lot of it. If we had really great rocket technology, we wouldn't need a space elevator. So there's a limit, there's a trade-off on how many rocket flights we're going to use. We could do more, and we have a stronger, faster, safer ribbon quicker, but it would cost more money, so there's all those trade-offs. Once you get it assembled, and whether you do it robotically or whether you do it with humans, and there's pros and cons for either one, once you get it assembled, what you've got here is you have an energy source, a power beaming system, a laser, coming up from Earth. And what you've done is you've taken the solar panels, instead of pointing them up towards the sun, you flip them over so that the energy, you can beam the energy to it and keep a constant rate of energy, a controllable rate of energy on the system all the time. Yeah?
Since you're in low Earth orbit, how does the laser change the satellite? It's moving very fast.
Give me a second. Okay, you never actually move. The quick answer is you're not moving. You're mostly stationary. Because right here, you've got a rocket engine. You can see a little bit of the blue flame there. The Earth is spinning. You need, ultimately, when the ribbon is connected, you're going to be at a specific point on the Earth. Right now, you're not connected, so you have to use the rocket power to keep you in a geostationary position, even though you're not actually geostationary. Okay? Does that kind of answer the question? Okay. Bless you. Are tricky. Yes.
Yeah, because if you're adding energy, normally you are either changing altitude,
Right, and we are going to be doing that. Give me a second longer. All right, so what we're doing is we are providing an energy source to the solar panels. The solar panels are converting them to an engine, and you're moving out. Now what's happening is you can see it's starting to slowly push away from the Earth. The next process takes about 3 months, and you're doing a couple things all at the same time. You are moving away from the Earth slowly. You are dropping the ribbon down, and what's happening is as you're laying the ribbon out and you're getting further and further away, you're changing your center of mass moment by moment. You're doing it slowly, you're doing it gradually. The part of the ribbon that's going down is going to touch down on back in the atmosphere about 3 or 4 weeks after the process started. But the other end of it, the counterweight system, has to travel some 60,000 miles. It's going slowly. That's a really important detail because this is not like a rocket re-entry where it's all bumpy and fiery. We're only dropping the recovery cone at about 25 miles an hour. Now, I want to point out here that where we're going to locate this thing, tentatively, is about 2,000 miles south of San Diego, 2,500 miles west of Quito, Ecuador. There are some real advantages to being on the equator. One of them is that you've got less storms, the orbital mechanics get slightly easier. There's a whole bunch of other reasons. This part is a little bit wrong. We originally were going to use systems that were like the sea launch or like an oil platform. Since we started doing this research, it looks like that's probably not the direction we want to go, and I'll show you some revised versions here. We're dealing with 24/7, 365 current that's going westerly. Having this sort of structure is not very cost efficient, fuel efficient. And we need to be a little bit more maneuverable than these systems are. So we're actually switching to a ship. It actually looks like something like 2 oil rigs side by side. It's about 600 feet wide, 900 feet long, pontoons. It looks like a big catamaran, a really, really big catamaran. So everything that's on these 2 systems is actually going to be combined into one now. What you're going to do here is, now that you've launched that first ribbon, this is only 8 inches wide at this point, very fragile, very easy to break. This is when we're going to have some heart attack inducing moments, because you've already spent roughly $10 billion at this point, and this is the point where it is most likely to break. So one of our revised design scenarios is, instead of sending up 4 rockets with 4 payloads and 2 strings, we're going to send up 6 or 8 and have more string. So that gives us multiple points of failure instead of a single point of failure. It gets more complicated that way. It's slightly more expensive, but when you add in capital costs and the risk involved, it actually balances out pretty nicely. There was a question over here first. Oh. Sorry, go ahead.
Why 60,000 miles? Versus
You-
300 miles.
Right. You have to, again, it's always about balance. You have to get past geosynchronous in order to have the counterweight effect that you need. And the science fiction was always talking about grabbing a really large asteroid, repositioning it, and using that. The larger that counterweight, the smaller the string has to be. So what we're balancing is we are making our counterweight. It's a man-made structure, so that's limited by how much cargo we can carry up in a spacecraft, which, when you start figuring out how much raw tonnage we can use, that dictates part of the answer on the length of the string. The other part is, you've got that ball on the string again? Once you get past geosynchronous orbit, you start picking up energy. If you were to let go of that ball, it's going to fly. All right, there's a lot of stored energy in that ribbon. If you have a spacecraft and you get past geosynchronous, if you go a certain point, you're going to get released and go towards the moon.
That enables the tension.
Right, right. It also enables the destinations. Further past geo, you can go to the moon. Further, you can go to Mars. Further, you can go to the asteroids. Depending on where you let go on the string is added energy to your propulsion. Does that make sense? Okay. Go ahead. The laser beam is a free electron, so we're not free electron laser, so we're not really putting out much in the way of heat energy. We don't really expect much of a problem. That's an area that we're looking into. We don't have solid answers on that yet, but our first impressions are that it's going to be a non-event. Well, the weather, let me get to weather. I'm going to talk about weather a lot in a second. Hang on, and let me get back to this. No. Go ahead.
Okay. Why have the attach point over water instead of land? Is it vertical?
I'm going to answer that in a lot more detail. Give me a second. Give me what?
In low Earth orbit, you use like 1 G of rocket power to stay up, and you do that for over weeks.
Yeah, that's why. But you can't do that with rocket power. You have to bring your own energy, which is why we're using the laser as the energy source. You couldn't. The propellant's actually pretty easy, as long as you have a renewable source of energy. Okay. All right. So first, we're back to this. It's 8 inches wide. That's very fragile. Probably going to break. It probably has just a few months worth of lifespan at that width. The wider this thing is, the stronger it becomes. So that first process was about a 3-month process. The next part actually takes quite a bit, nearly 2.5 years. And what we're doing is, this piece here is what we're calling a construction climber or construction lifter. Again, powered by the same laser system that we had before. What we're doing is we are taking the original 8-inch wide ribbon and we're adding another piece to it. We're making it wider. Then we're adding another one, and then another one, and then another one. The same way that, let me stop this for a second. The same way that the Romans would cross canyons, they'd take a bow and arrow, shoot a string across, they'd pull another string across, and another string across, and they would slowly build up that into a bridge. We're doing essentially the same thing here. That first 8-inch wide ribbon becomes around 3 feet wide when the first phase is done. The wider you make that ribbon, the stronger you get, the more cargo you've got, the more safety you've got, the more opportunities you have with sending up cargo. If you make it really wide, like say 10 feet wide, you can then split the bottom off, and so you have a up ribbon that's going up, and then you've got a down ribbon on the other side, and then you kind of build up again. Yeah.
Now you're only playing with width. You're not playing with thickness at all?
No. And thickness, let's go back to the original science fiction. They were always talking about great big cables. Sometimes they were 30 feet across. Carbon nanotubes are really strong, and they would not need to be that thick. So you're talking about a relatively thin cable if you were to do it that way. But you've got a whole bunch of problems. You've got specifically orbital debris and micrometeors. All right, if you've got a cable and you've pierced on the side, you've got a fairly major structural breach. But if you have a ribbon and that same meteor hits in the center of it or the side of it or something like that, it's relatively minor over the entire structural integrity. So that's kind of why we're going width as opposed to thickness, because one, it's easier to construct that way, and two, it adds to some of the structural requirements that we need. Also, over time, you've got all this orbital debris. You're going to have minor punctures through this thing all the time. By making it wider and wider and wider, it allows us to either abandon or to destroy the part that's not safe anymore. And you wouldn't be able to do that if you were a cable. You can. It's actually easier to build than it is to repair. Okay, maybe not. We think it is easier to keep widening, because these, once we're going to have to make about 260 trips with these. We're going to know how to make those pretty easily. We're going to understand how they work, and it's pretty straightforward to add another piece. Now, there's some complications. I don't want to gloss over this. All right. I've said many times that while we don't see any showstoppers right now, there's a couple areas that we're a little concerned about. That I don't believe we have asked all the questions, let alone have all the answers yet. Okay, I think we've still got a couple more years of development. But there's some stages to this, and we'll talk about that in a minute. This is our construction lifter, and you can see our design has changed dramatically since this was originally built, and I'll show you some of this stuff over here in a little bit. But the basics are pretty straightforward. You've got rollers, you've got an energy system on the back, you've got the power source, well, it's not really a source. You've got the power collector at the bottom, and that makes up the construction process. As you add in, the yellow is being added to the gray. That's the new material that's widening and strengthening the system. The cargo lifters are actually going to be fairly different from this, but the basics are still the same. You're still going to have a drive system. You're still going to have a power requirement. You're still going to have balance issues. So that's the basic construction process. This whole process takes roughly 3 years. We feel it's probably about a 15-year project. The first several, the ones that we're in now, are research and development, building infrastructure, getting our political and legal and financial ducks in a row. There are, like I say, there are still some questions that have to be answered, and that's essentially where we're at now. Any questions on this part? Yeah, go ahead.
Why take so long? Why not just run, why not build 100 construction lifters and run, head and tail, and widen the thing, half an inch, I don't know what that adds, a quarter inch or a tenth of an inch.
It's about balance. What this can do, that first 8-inch wide lifter can only carry about 200 kilograms worth of cargo. It's so light and so thin and so fragile that it can't carry very much up it. So that limits how much new material you can add to it. Does that make sense? Okay. So that's really why it is. Once you start getting, those first couple months, it's only taking just that much. It's only taking just a fraction of what it's going to eventually take. The last couple months, it's taking sheets like this, and because that's just a factor of how much balance we've got, how much strength we've got, how much load capacity it can carry, which is also why we're looking at, instead of this is a 2-ribbon system as this was designed. You brought 2 down, you zipped them together, and that started your first 8-inch wide ribbon. What we're looking at is actually bringing in 4 or 6 ribbons right from the beginning which would make this whole process much faster. It would actually probably cut 2 years off the construction time and make the whole thing safer and more likely to work. But now you've got 6 ribbons you have to manage as they come back into the atmosphere. You've got to, tie them together correctly. I mean, heaven forbid you tie them backwards or something. I mean, so there's trade-offs, and I know that's what we're always balancing trade-offs.
No way to zip them in orbit before you drop them through the atmosphere?
That's been suggested. It's complicated, but the whole thing is complicated. So it hasn't been ruled out, but honestly, it hasn't been looked at very seriously yet. It's actually really not a relatively new idea for us. One of the big questions is this thing. It's flexible. So you're adding, you've got this that's in place, and it's mostly rigid because of the balancing forces. You're adding a new ribbon. Well, this is going to flex. How do you tie them up? So it might be easier to do it in orbit. So that's one of the things that are being considered. The oscillations of this ribbon are actually really, really challenging. Our first cut of this was pretty elementary, and the more we looked at it, the more challenging the oscillations become. Yeah.
Can you talk a little bit more about how you zip the ribbons together?
I can give you really general information about that. I'll try. Give me a second on that. Let me talk a little bit about the carbon nanotubes, and that'll help make it a little more clear. Let's talk about that. All right, so the thing that made this whole idea remotely possible was the strength inherent in carbon nanotubes. What they are is a diamond is one of the strongest structures because of the way the molecular bonds of carbon form. And carbon nanotubes are ridiculously small tubes of carbon, about 1/5 the size of a human blood cell. That's how small they are. And they've been tested to be about 20 times stronger than steel so far. They're theorized to be probably 100 times stronger than steel, but that's at the ridiculously small level that's not very useful. You have to then take that powder and functionalize it somehow, which right now is a challenge, but we're starting to see solutions to those challenges. So what we're doing, and when I say we, by the way, I don't want to imply that it's just me. I mean, there's probably, ISR probably has 70 people working on different aspects. Edwards probably has a team of 6 or 8 dedicated to this. We have research relationships all over the place at MIT and Stanford and Harvard and Air Force Research Lab and Department of Defense. And there's a whole bunch of different organizations working on this. Most of them are coming together the end of this month out in Washington, D.C. for our 3rd annual conference. So what I'm showing you first is stuff that came from the University of Kentucky. What they did is they created raw carbon nanotubes, which a year ago, this was state of the art. I'll tell you something that's changed since then. They created raw carbon nanotubes, and there's about 150 research groups around the country around the planet that are working on carbon nanotube work there at any significant level. The raw stuff looks like something that would come out of your fireplace. It looks like soot. It's carbon. All right, and heck, it was made at 2,500 degrees Celsius, so, I mean, it really looks like soot. Then the soot itself is not very useful, so then you have to functionalize it. And what you do then is you drop it into a matrix, a composite like fiberglass is made, where you've got, a glue and a fiber. With dropping into just a 2% addition of carbon nanotubes into standard polypropylene plastic, create a 40% increase in strength. All right. What we're looking at is, what we need is something about 15 times, 20 times stronger than steel, to kind of give you perspective here. So we're not close yet. We're probably, I'd say 3 years from having a material that we think will do the job. Once you put it into plastic, you can do a lot of interesting stuff with it. And my job, I told you I'm the business development guy, is my job is to figure out how to make this company profitable, whether the space elevator succeeds or not. All right? And so this is one of the things that we're betting on, is if you can take carbon nanotubes, drop them into a matrix of some sort, you can make a car body that's our first check. Everybody smiles when I look at that, when they see that, but that's our first revenue. So it's not much, but we're getting there. It's actually a little bit better than that, but that's our first one. Yeah, we're actually a space company with revenues. That's pretty rare. So we take the carbon nanotubes and you can put them into a car body, which makes for a lighter car, so it's more fuel efficient, and it's stronger, so it's safer to drive. You know, Boeing, our next door neighbor, is one of the largest users of carbon composites in the world, so we think they're going to be pretty interested in this stuff when we get ready for it. So I'm going to pass these around. This one that looks empty is not. It's a fiber that's about a fourth the thickness of your hair, and we spun this out we can spin this out at kilometers an hour now, so it's pretty easy stuff. We haven't made the press with it yet, though. Right now, Rensselaer and Rice are the guys who are, quote unquote, the leaders in carbon nanotubes, but that's just because we haven't publicized stuff. And this stuff was created with a multi-million-dollar laser. Well, there's two kinds, and you can't tell the difference, so it doesn't matter. But one of them was created with a multi-million-dollar laser. It could create grams a day. I mean, ridiculously small amounts, not very useful. The other kind was created in a furnace that cost around $400,000. Again, could create grams per day. Well, if you're going to make a material that's 60,000 miles long, grams a day are not going to cut it. So one of the areas that we're looking at is mass production. And we just stumbled across some research that I'm hopefully going to have the rights to next week, that you get the purity of the laser-produced stuff, 99% pure, for 25 grand per setup. So we're pretty excited about that stuff. So I'm going to pass these around. There's 4 of them. They're not all that interesting, but, you know, we can... and also on the plastic, we can make sheets of it. By the way, don't open those. And I'm also going to pass around, this is standard industrial carbon. The hairs on it are really, really, really fine. You can easily pull it apart this way and break it. If you try to pull this way, I'm betting nobody in this room can break this. So, this is what the about 20 years ago, this is what they thought they were going to make the space elevator out of, but it's not strong enough even then. Okay, so back to your question about how do we zip this stuff together. Because we're embedding it into plastic, and right now, by the way, we don't think the plastic is the end result. That's not going to probably be the end material that we use. But because of the methods that we're using to create the ribbon, we feel it's pretty likely that we're going to be able to melt the two together. And there's still some big questions about that. So that doesn't really answer your question, but that's as far as we've got on that particular problem. What time is it? Okay. I am going to go over some of Dr. Edwards' slides. Part of this was, that phone number doesn't work. Sorry. But that's the right email address. I didn't realize that was still up there. Dr. Edwards did some of the original work on this. He received nearly $600,000 in NASA grants, NASA funding. He's now out at the Institute for Scientific Research. He's got another $2.5 million to work with out there. We're in the process of fundraising ourselves. We hope we're going to have significantly more than that. But Edwards and I used to work together. Last year we worked together, a year and a half ago we worked for a year together with Hylas Systems. And so maybe some of you saw some of the press about that about 2 summers ago. When Edwards was doing his original research, he had a pretty good understanding of the physics and math involved. He didn't really have much of an understanding of the business development, the marketing, the political science, the legal issues involved. He brought me in on part of that. He and I co-founded Hylas Systems. When the NASA funding ran out, we had a fairly major disagreement on how to proceed. He wanted to go back in the lab. He felt this should be a government-financed project. I felt it should be a capitalist-driven project. So we split ways. He's out in West Virginia. He's still doing all the research and development on his end, all the technical development. I'm still working on the commercial end. So, and like I say, I'm going out to the conference in a few weeks out to DC to kind of see the state of things. This slide always surprises me, even though I've seen it a million times. This is the original Challenger explosion, and when we first started working on this, the Columbia hadn't blown up. When the Columbia exploded, crashed, however, I mean, everybody calls it an accident, and I hate that term. It was a crash, all right, one way or another. And when the Columbia crashed, it actually helped our project, and I'm surprised by that. But as soon as that happened, people started asking, is there a safer, better way? And we think that there is. Overall, the system will have a 20-ton capacity. How we configure that, you were asking earlier about, why not just send up a whole bunch all at once? With this system, we're designing it for, well, we're really over-engineering it, but we're designing it for 20-ton carrying capacity, and that's about 7 tons worth of infrastructure of the lifter itself. And then we can configure it a couple different ways. We can send up 13-ton payloads every 3 days or 5-ton payloads every day. I tend to aim for the 5 tons every day. To put that in perspective, a standard cargo train, is going to dwarf our carrying capacity, all right? But our carrying capacity dwarfs the current space capacity. We feel that we're going to be able to launch about 10 times the global access to space our very first year. And then if we continue to build up, make the ribbon wider, we're going to be able to build even further than that. One of the really great things about the space elevator, since you're not bringing up your fuel, you're beaming it from the ground, it's relatively inexpensive. This structure is the only one where economies of scale play into space access. You can use rockets, and you can build rockets all day long. You can have 1,000 rockets a day. Economies of scale are going to factor into the production of the rockets, but they will never factor into the fuel requirements. So that's what makes this system so appealing. Once you've got it in place, you can open up the inner solar system because you can make more of them at a really reduced price. Hang on a second. Our goal is to build the first one. But once the first one is in place, it's easy to make the next one. And the one after that is cheaper and bigger. And the one after that is cheaper and bigger. Because you can use the first one to carry all the requirements for the second one. That makes it, that simplifies the whole process. 1 week travel time to GEO. Some people think that's really long. You're only talking about a couple hours to get to low Earth orbit. you're only talking about a couple hours to get to low Earth orbit. Rockets, when they get to low Earth orbit, have got momentum. If you dropped off at low Earth orbit a couple hundred miles down, up, you're going to fall like a brick. Okay? So, yes, it only takes a little while to get into space, but you don't have any momentum. So you're still going to use rockets when you get to a certain altitude, whether you get off at low Earth orbit, whether you get geosynchronous orbit, or if you've got a moon or a Mars trajectory, you're still going to use rockets. You're just going to use them in a different way. When people talk about a week to get to geosynchronous, they assume that that's a really long time. But the fact is, most rockets take 4 or 5 days to finalize their orbit to geo anyway. They take a big boost to get up, and then it takes a couple redirectional boosts to get in the right spot. So you're still talking roughly the same time frame. And instead of a big, jarring, loud, painful, bone-breaking trip into space, and believe me, a lot of those electronics fail long before they ever got to space because of the rattle. We're going up at, we start at 35 miles an hour, we climb to a maximum of 125 miles an hour. So if your equipment, if your body can survive a car going pretty quickly, you can last on a space elevator. And that opens up a whole set of interesting possibilities. Hang on, there was one here first. Go ahead. Oh, sorry. Yeah?
Are you saying that once you get the first one built, the future space elevators would deploy wide ribbons right off the bat rather than building? So that's where the economy is. Otherwise, that seems like the hard part.
Right. The first one is the hard part. After that, it's easy. Yeah.
The ribbons seem like the hard part. That's where your bottom.
No, the ribbon's easy. I mean, are you saying it's hard because it's long, or are you saying it's hard because it's getting
like
into place?
Years to build it.
Yeah. Once you get the first one up, you use the carrying capacity of the lifter in the first place, carry up a new ribbon.
It's wide.
Well, it's part of that whole construction process. This one brings another ribbon here and builds up. Does that make sense?
So you wouldn't actually build multiple elevators, you just keep making the ribbon wide?
You'd actually make multiple, for safety. What happens is you build up the one, like we zipped it the first time, we unzip it the second time and pull them apart. Okay, so you have the first one that might be 5 tons a day cargo capacity. You make it wider, so it's now 25 tons because it's really wide. You split it, and now because of the math, you're actually probably back to 10 tons apiece. But now you've got an up system and a down system. And then you take those and you can replicate those again and again and again. Actually, the tricky part there is actually finding an ideal location. There are not very many places in the world you can put this thing. Mm-hmm. So that's actually a limiting factor. There's also another couple limiting factors. There's only 1,800 sanctioned satellite slots around the planet, well, in our orbit, I should say. And most of them are full. So we have to not only find a place on Earth that's going to work, we also have to find a spot up above that's empty. So that's where some of the political, legal stuff comes into play.
Percentage increment you can add onto the ribbon based on what's already there. So for an 8-inch ribbon, can you add like 1%, 5%?
You're usually looking around 3 to 5% of what's currently there is what you can add. So it is a slow process. Well, in the first one, how am I saying this? The first one we're going really, really conservatively. Once the system is in place, we'll have a better understanding of some of the factors. I think we can build up fairly quickly. If you've got 13 tons worth of cargo capacity, that's a lot of ribbon. The ribbon only weighs, by the way, ribbon only weighs about 25 to 30 pounds per mile. So, you've got 13 tons. I haven't done the math, but you've got a lot you can bring up there.
That's for what width?
I don't know. That's the full 3-foot wide width. That's the full system. Is about 25 to 30 pounds Okay. Yeah, go ahead.
You said beam up. How does it?
You're beaming the power. You've got the solar energy. What we're doing is we're taking just straight old standard diesel, converting into laser energy, beaming the laser energy up to the solar panels on the bottom, and that drives the motor, and that's what drives the traction system.
Propels the platform up.
Great segue into robots. Okay. Give me a second. Let me come. Yeah.
There's a piece where millimeters of cross section.
Yeah.
So if it's 3 feet wide, how, I mean, that's...
It's paper thin.
It's paper thin.
It is paper thin.
Okay.
In fact, going back to the whole science fiction idea, they were talking about, 30, 50 feet across. This stuff is that strong. I mean, it's really, it's mind-boggling how strong this stuff could become. Where we're at in the technology development, by the way, is the stuff didn't exist 11 years ago. The stuff wasn't able to be put into a usable form 5 years ago. We're now flirting with being stronger than Kevlar. Kevlar is stronger than steel by weight, and we think we're going to be beating Kevlar within months. Steel, there's a lot of different ways of measuring strength. Gigapascals is one of them in tensile strength. Steel is usually, industrial steel is usually considered 3 gigapascals strong, GPa strong. Kevlar, Kevlar's in the 3.7 range. Some of the spectrum materials are in the 4s, the low 4s. There are some silicon derivatives that are in the 5s range. But that's it. That is the maximum strength that we know how to make right now. So in just 11 years, we've gone from impossible to flirting with one of the second strongest material out there. And there's somebody working on something that might be able to pull 12 GPa within the next year. So more than double the strength of steel in a really short time. This is as big a deal as going from the stone to the bone age, or the bone to the stone age, or the steel age. I mean, this is a major advancement in material sciences. I'm gonna fly through this, and then I'm gonna get some questions on. I'm gonna start working on. I'll show off some of the robot. So this kind of gives you an idea. This is the hexagonal structure of carbon nanotubes. They're ridiculously small. You can't even see this. That's one thread. That's actually, 2 years ago, this thread was nearly state-of-the-art. Now, like I said, we can make this stuff at kilometers an hour. That's the design of it. It's going to be flexible, and there'll be some cross members, but they'll be flexible also, and we call them tape sandwiches. We're just going to take a whole bunch of straight fibers and every so often connect them. We already talked about the deployment. We talked about the spacecraft. If anybody, you were wondering about, how do we stay up there? It's a magnetoplasmic. I can't even say this thing. It's an MPD drive, if anybody cares. Sorry. Talked about that. Power beaming. All right. Power beaming is actually one of the linchpins. This is a problem here. The Army Ballistics Lab has spent pretty close to $700 million to $1 billion on their Miracle laser, and it's not as strong as we need, and it doesn't work very well. So that's one of those, we keep blithely saying, oh, we're going to power this by laser, but we don't have a laser that will work yet. What we're basing this on is telescope work that has to keep retracking stars. It's got error-correcting systems in place, and it moves pretty fast, and so that part will work. Talked about that. All right, what are we going to do with it? All right, great, we built it. We got access to space. It's cool. Now what? We're going to do what we've always been doing, which is launch satellites. We're going to just do it better faster, cheaper, safer. And most of them, instead of going to low Earth orbit, which is where they're going now, they're going to go probably to geosynchronous orbit. Because they're not restricted, because we don't restrict them based on weight, they're more efficient in the stable orbited geo. So that's probably what's going to happen. Another area that's pretty interesting is solar energy satellites. We're going to put great big, and when I say we're going to provide the railroad system to the destination, and somebody else is going to make these things, we think. Huge solar arrays up in space, collecting energy, using nearly the same power beaming system, beam that power back down to Earth. As the world is spinning, it provides clean, limitless, virtually free once the system is in place, but I guarantee the electric companies will charge you. Renewable energy. As the world is spinning, peak rates always happen in the evening when you need to turn on the lights. So as the world is spinning, we can beam power back to London and to New York and to Chicago, and as the world's spinning, we can get peak rates all the time with a renewable energy source. You can then take the same renewable energy source and beam it into the outback of Australia, out into the mountains of China, out into Africa, places that there isn't, consistent power grids. So there's a lot of opportunity there. We actually feel that maybe the energy companies might be really interested in helping finance this thing. We've already went out and spoke to British Petroleum. BP Solar is a division. They've gone on record saying, yeah, they think this is a pretty interesting idea, and they're tracking this. So we're pretty happy with that. Everybody talks about the hotels in space. I am less of a fan of that than most of my colleagues. I think it's neat and it's cool and it's going to spark the imagination. I don't think the revenues are there to support it, and that's my job to figure out how to pay for this thing. If Disneyland wants to make a resort up there, I'm all for supporting that. But the early model, the first 5, 10, 15 years of construction, or after construction, 15 years after completion, it's going to take a while before you start getting a lot of people up there. What you are going to have, just a second, what you are going to have is, I don't want to leave that. What you are going to have is factories. I think you're going to have huge telecommunication systems up there. I think you're going to have factories for pharmaceuticals. I think you're probably going to have facilities for health and biosciences. Those things are going to start happening, and you're going to have people go up there for that. There's a lot of talk about going to Mars, and we talked about you've got all that excess energy. You can just fly to Mars pretty easily. Our Earth has got a 23-degree tilt to the plane of the solar system, so we're on the equator. We're actually being thrown slightly the wrong direction. We need to be here, and we're being thrown there. So we're still going to have plane change rockets to get us to where we want to go. But it opens up a lot of stuff up there. Not done.
I don't understand. How do you get to Mars then?
Okay.
You extend a ribbon all the way to Mars?
No. Wow, that's a long ribbon. No, you can't do that. What you've got is you've got that ball on the string. If you let go of that ball, it is going to fly, right? You've got all that built-up energy. So if you're on the string, you don't feel the energy. But as soon as you let go, that transfers you out. So that gives you momentum.
That's the launching mechanism?
That is part of the launching mechanism. You still need rockets because you're going slightly the wrong direction. You're going down as opposed to out. But it gives you a big boost in the right direction. So that's part of the equation. Okay. These are our Murphys. This is all the things that can go wrong. And let me tell you, this is not all the things that can go wrong. Whoops, sorry about that. Okay. The number one question, by the way, is not on this. The number one question is, what if a plane flies into it? I think that's we started really making a splash recently after 9/11, so that was really in the American psyche. we're hundreds of miles from air routes and sea routes at our preferred location. So we're going to know long before anything happens if there's a plane that's not supposed to be there. If it does hit it, it's probably going to break. It's going to bring the plane down. It's going to be bad. I'll talk about the recovery scenarios in a second. It's a big question about lightning. That's one of the reasons why we're picking the location that we are, because in 10 years I've never recorded lightning here. We've got two equally credentialed experts. One says we will never be able to build it because we will always be hit by lightning. The other one says we will never be hit by lightning because it'll dissipate any charge in the area. And honestly, that's not something we're going to risk $10 billion on until we know the answer to. So we're looking at that. Wind is actually not much of a factor. Out of this entire length, only about 15 miles are actually within the wind zone. Once you get above in the higher atmosphere, you're not really subject to it. And winds at a tropical location tend to dissipate. Storms can't cross the equator because of the Coriolis effect. So about 7 degrees plus or minus the equator, all of the hurricanes, typhoons start to lighten. So by the time they get to us, there's nothing, they can't get to us is what I'm saying. Okay? Radiation and atomic oxygen. If the material to make the space elevator was considered unobtainium once upon a time, we now have to consider super unobtainium because we have to deal with radiation problems and atomic oxygen. Atomic oxygen, we can cover the system. There's a particular area that we're going to be susceptible at the high altitudes. We can cover that area pretty easily, so we think we've got solutions for that. Somebody asked about why being on a boat. I don't remember who that was. Okay. Why being on a boat? That is because of our oscillations and also low Earth orbit objects and also for orbital debris. Being on a boat allows us to move. So if we move the bottom, the ripple effects will move the top. Okay. Right around here, in the about to 200 to 500 mile range, there's a lot of orbital debris, hundreds of thousands of pieces of orbital debris, some of which are the size of paint flecks, some of which are the size of pencils, some of which are the size of a chair. We have to avoid those. By moving the bottom, we are able to move the top, and that's one of the reasons why we're on a ship. Also, there is no land-based location that is lightning-free. None. There are some areas up in the extremes, the North and South Pole, but those get complicated for other reasons, so we ruled them out. So that's why we're going on a ship. Okay. Oh.
What's going on a ship for your geopolitical issues?
I would like to say I have the answer to that. I have good guesses. It's international waters for sure. Right now we're going to build this as a U.S. flagged ship. I believe it will not be built without the direct participation of both the Air Force and the Navy. So they're going to be around the area. But I also believe it will not be built unless we have international public support. So we're hoping to build allies along the way. I mean, well, okay, think about how much capacity we have. We have so much spare capacity that all the U.S. demand, all of the commercial and military demand is only a few payloads. We have nearly a year's worth of daily flights, lifts, to work with. So we actually can give our spare capacity away to developing nations, to corporations that want to have their own access. If Microsoft wants a satellite, let me know. But seriously, that's how much spare capacity that we have. We can go to large organizations, universities, schools, companies, smaller nations, and we can say, look, we'll give you capacity. And so that, we think, will help us generate allies.
You've already got a problem with the amount of credit that's up in GEO. now you're going to introduce 20 tons of credit at a time, or 13 tons of credit.
Well, actually, we're actually only going to take things to GEO for that particular reason. If you don't want to go to GEO, you have to go to rockets.
So you're not going to do any LEO drop-off. You won't resupply the ISS. You won't.
Well, the ISS will be gone before we get there, probably. We've got 14 more years to go, and I'd be really surprised if that was still sticking around. But despite their plans, I know their plans say it's going to be there. No, I mean, I'm not going to say no, we're not ever going to bring low Earth orbit cargo, but we're going to be a lot more reluctant to do it, because that's one more thing we have to dodge. Factor in the fuel costs of a 600 by 900 foot ship, move it once. How much does that cost me? Then I have to balance that against, is the payload worth it? Every single time I have to move that ship, because that payload is going to pass my trajectory. And every low Earth orbit object is going to pass our trajectory. So I just think that's not very likely to happen.
Planes are just worth cleaning LEO.
NASA's talking about it, and I'm going to take a slight segue because it does matter to me. When I first heard about this, I thought they were really joking. But, I mean, I'm working on a space elevator, so I have to have a fairly open mind. They are talking about really large pieces of bubble wrap, bringing it up into space, leaving it there. I mean, like, huge, room-sized pieces of bubble wrap, where these paint flecks will come in, and they're going several miles an hour, 5 miles, 10 miles, 1,000 miles an hour. They're going to hit this bubble wrap, and they're going to puncture the first one, and the fourth one, and the 400th one. But each one they puncture, they're going to lose energy, and at some point they're going to get stuck in the middle of the bubble wrap. They are really looking at this problem. So I am not commenting on their solution. I'm just saying that is one that is getting a lot of attention. Okay? That's pretty much my presentation. We're looking at a total price tag of about $7 billion. That's going to be split between government funds, private equity, and debt. We're a long ways from it. We're out there. Edwards is looking for money on his side. I'm looking for money on my side. It's an ongoing battle. We've got some support in Congress. We've got some support at the Department of Defense. From 3 years ago, this was a mythical idea with huge giggle factor. Now, there are some people taking it seriously. So that's one of the things we have to kind of overcome is, we've come a long ways, we still have to go a long ways. Raising capital is going to be the thing that makes this or not. Yeah.
I have a really good imagination of the path and the infrastructure context, but I don't have a good sense of the element.
This is Frankenstein. We call him Frankie because he's dumb, he's ugly, and he's slow. But it's our test platform, and we've done a lot. We started out with Legos on the far side over there. We went to Legos on purpose. Legos allow us to be creative without the engineering restrictions. Yeah. Legos allow us to be creative without the restrictions of having to worry about silly things like engineering. Okay, we spent a couple grand on Legos, and we started making and taking them apart and putting them together and taking them apart. And really, it was a lot of fun, but there was actually a lot of learning involved with that process. Because one of the things that we didn't know that we know now is a guide system is essential. Every time we started building these things, it would go off the ribbon. And we'd build something and kind of keep it there, and it would go off the ribbon again. So Legos allowed us to learn some fairly important stuff right from the beginning. What you're looking at is there are 2 tread systems through here. What you're doing is you're gripping the ribbon. You've got a battery. In this case, you've got a battery system because we don't want to mess with lasers in the office. And you've got a guide system at the top and the bottom. The batteries charge the motor spins the wheels are clamped onto the ribbon, and that's what climbs. And so this is the core structure. Now, you can add a whole bunch of stuff onto it. Eventually, you're going to have solar panels out here to catch the power. And by the way, if anybody's really interested in this stuff, come the end of the month, there's going to be a pretty big announcement on a $1 million challenge for creating a robot that'll climb. I think they're looking at 10 kilometers, but I'm not sure. So there's a pretty big robotics challenge that's coming up really soon. But this is the basic core concept. Anything else you add to this is just a refinement of the basic process. Do you have the other one? Do you have the... Okay, so in the process of doing this, we found out a couple things. One, that one motor and one drive system is really a bad design. The tread is really good. Say, having one of these doesn't work very well. One of the problems we were always having is getting this tolerance, because the belts just keep slipping. No matter what we do, over time, we can't keep enough pressure on to keep the system in alignment. We looked at chain, we looked at a bunch of things, and frankly, this design just simply doesn't work very well. So we're redesigning it. This will actually fly on a hot air balloon. I mean, this is what it looks like, we think, in our imagination down the road. I can't stop on this one right here, but that's probably what the elevator itself will look like, the car itself. We call it lifters. This will probably fly in a hot air balloon sometime in the next few weeks. What we're doing is we're just dropping the thread through here. We've got 5 sets of wheels. We attached the motors to each of these. We found really great motors recently. And so that's what we're working on. By the way, what we're doing with this whole process is a modular design. We're working on one piece at a time. We're pretty comfortable with the guide systems at this point. Now we're really trying to refine the drive system. So, yeah.
Have you guys thought about ice build-up on the planet?
Yes, we have. Somebody asked earlier about what if the laser hits the ribbon. It doesn't generate a lot of heat. It generates enough heat for the to push the ice off. We actually don't think there's going to be, again, out of the whole system, ice is only a really small factor in it. There's only the first few miles where ice can even form. So, yes, we have to deal with it within that area, but we think that's a pretty easy one to solve. Lots of ideas have come up with that, the laser being the first one, but we actually can have a blower heater system right above. Just the drivetrain itself is important. All the other pieces matter too, and so the longer this thing is, the more control you've got. And so it makes a lot of sense. Somebody was asking about repair. Have a sensor array in front to see if there's a problem, see if there's a tear or a rip. You could use that same sensor array for heat and clean.
Do you expect 52 payloads a year, or do you have several going up at the same time?
You'll have several going up at the same time. Again, it's a question of balance. Once you get to a certain point, you've reduced gravity a certain amount, you can drop another payload on. You send 2 up. They've gotten to a certain point, the gravity is reduced on those, you can send up the 3rd. You can actually have 5 at a time on the ribbon, which is how we get 5 tons a day of capacity. Okay.
What's going to provide the horizontal force to bring it up to orbital velocity?
In the original design, the original construction stage, or once the thing's in place?
Both.
Well, in the original construction stage, we've got a rocket to add that in. Once it's in place, you don't have to mess with that anymore, because you're balancing the spin of the Earth is providing
I
that.
mean, something is like so is the cable going to bend sideways then to?
Yeah, the cable's actually going to go like this. So here's the Earth. The cable's going to go kind of like this. The oscillations are because we're moving the ship. We're on a 10-kilometer-an-hour current. We're avoiding orbital debris. There's oscillations are in there. Every time the moon goes past, it plucks a thing like a guitar string. The oscillations will happen a lot. But as the Earth is spinning, that's what imparts the angular momentum. Does that make sense?
So then, what about will a counterweight at the top be pushed westward? Then do you have to have like a control, any sort of active?
The center of gravity is in orbit.
Right.
Yeah, but as you bring stuff up into orbit, you have to add more angular momentum to it, right?
Presumably, that's a small fraction of the overall weight of the entire system. So.
Right. Your whole system is 800 tons. You're only moving 5. So you've got.
If you're bringing 20 tons in a week, then.
Well, you know what you're actually doing is you're actually slowing the spin of the Earth. That's where you lose the energy. You're actually, but I mean, you have to move. You'd have to move Australia to notice it. Okay. But you're right. You do lose a little bit every time you move it. You send something up. You've got to deal with that. But the Earth is a lot bigger than our system is, so that's what kind of counting it.
Push the ship. Right. It's not actually anchored on the Earth.
Well, no. Moving the ship doesn't really affect it. Our ship. How can I say this beyond balance?
What actually transfers from that to the Earth?
I can't answer that question.
You got to push the ship. You have to put engine from the ship, but that's easy.
Yeah, well, yeah. You're staying stationary to the Earth by the ship. There's talk about anchoring it all the way to the bottom of the ship, where we need the mobility. Way in the back.
Yeah, this may sound like a political question. It's actually not.
Okay.
But if this material is as strong as or will be as strong as you have said it will be,
right,
why hasn't it been nabbed and classified?
There's been lots of talk about it. There's been lots of talk. Edwards and I made a really specific decision about 2 years ago to make our project public. That's why we went to the Seattle Times. That's why we went to CNN. That's why we went to the New York Times. Because early on, there was some real talk at DARPA and Air Force Research Lab and a couple other places about classifying the entire project, which I thought was ridiculous. It's 62,000 miles long. You can't not see it. But, okay, this is a balance of power technology. The materials alone are a balance of power technology. We already know that there's a couple classified projects on carbon nanotubes. We know about them. We've heard rumor about the results. There's one that's mind-boggling, but I don't have access to it. So yeah, those are happening. What's interesting about our project is researchers that are not talking to themselves, talking amongst themselves, are talking to us because they think our project is cool. So we have gotten this stuff that came out of the National Renewable Energy Lab a few months ago. Somebody stumbled across it. It was an accidental find. The grad student emails me and said, hey, I figured this out. Will it help you? And I hired him on the spot. I'm going to Denver to negotiate an agreement. It's that good. But people are not talking in the community to each other because their research credentials are on the line. You've got to publish first. So they're not communicating, but they're coming to me. So there's things that I think I know that I would say Uncle Sam probably doesn't know. On the other side, my brother thinks I have a big target on my head. On the other side of that, I know also that China is really spending some money in the carbon nanotube research field. I've stumbled across the researchers a couple times. They've either preceded me at a location or come right behind me at a location. And it's totally funded by the Chinese military. So, I actually don't think Uncle Sam is paying quite enough attention to that. But
Yeah, I mean, it's really easy to think of applications for an incredibly strong light
right, I mean,
material.
think of anything that they'll get an advantage if it's stronger or lighter or both. There's some strategic questions in there. What can you do with a bomber? But really, there's day-to-day questions. What can you build in buildings? Like, we've got these great big columns in the middle of this building to support the building. What if it only had to be that big? What if it didn't need to be there at all and you could support the entire building from the edges? I mean, you're talking about changing everything about how we build everything. So, yeah, it's a political question. It's also a commercial question. It's a legal question. And, yeah, it's not an easy one to answer. Just a second. I'm going to... we only have a little bit longer. I'm not going to call on the people that have already asked questions. So I want to give everybody else a chance to say.
You deliver a lot of payloads at GEO. Is there a proposal for how you get them where you really want them? You certainly don't want hundreds and hundreds of satellites clustered around your elevator.
Right. There is an advantage to having lots of stuff at one location. Historically, we kind of think of this as St. Louis, the jump-off point to go west. A lot happened there, and that changed. Chicago for a while, and St. Louis, and as you got further and further, the center kind of grew. But there is going to be a pretty large cluster there. If there is a Disneyland, it's going to that cluster. If there is an Olympics, by the way, Olympics keeps coming up as a common topic. You're going to have clusters, and they're going to have real economic value. But you're right, you can't, if you want to see the other side of the Earth, that's not going to do any good. So you're still going to rely on rocket technology. We're going to provide linkage from A to B, and then Boeing and Lockheed will get you from B to C, or D, or E, or F. Okay, that's what we think is going to happen. I mean, we're not going to be. We're gonna help get people to and from space, but once they get there, I think the market is going to drive a lot of what happens, and so they're going to need rocket technology to get there.
Really a lot about how you get away from the ribbon without endangering it.
You're going pretty slow. It's actually pretty easy to catch. Like, okay, so here's the ribbon, here's the midpoint. You come up, you get caught. We're going to be able to control our speed on these motors. So we slow down, we get stopped, a gentle push. I mean, the joke is we kick them. Okay? I mean, we're not really talking about a lot of energy. Once you get a safe distance, and I don't know what that is right now, once you get to a safe distance, you engage the rockets and you go away. It's pretty, that part's pretty straightforward. Yep.
Different altitude. You're only going to stay in the same spot if you're at geosync, right?
Right.
If you're below or above, you're going to go flying off in one direction or the other, depending on whether you're above or below.
That's the answer. Clear? Yep.
What's the acceleration?
I got to ask people, sorry, I mean, I apologize, I'll try and answer later, but
What's the reality factor here? I mean, the money, based on what you described here, it pays for itself very, very quickly.
I think so.
So, you talked about the laser, you don't have it. Is this it? If you have the laser, we're building the same, we can bet on the same? I'm going to see this.
I mean, we've got a countdown clock on our website. Liftport.com, top right-hand corner, we got 5,059 days. I mean, we are that serious about doing this. But yeah, I think it's there. I think you've got four essential problems lumped together. You've got science and technology, you've got finance, you've got legal, and you've got political. We think that the science and technology is so valuable that the money is going to be easy. So that's part of it. Then you've got technical, or legal and political problems, which we've only just recently started working on. But yeah, the laser is really tricky. You don't need unobtainium; you need super unobtainium. I mean, there's still some real challenges here, but I think we have not seen any showstoppers, which I'm surprised after nearly 2 years of my work and a year plus that Edwards was working on it. And there's a lot of people working on different parts of this. We have not seen any showstoppers. I would say that the number one concern that we have right now is thermal expansion on the ribbon, which is a really open question, and the oscillations of the ribbon. We just cannot predict, we can't computer model the oscillations. I mean, we don't even have a guess how to do that yet. So prior to, assuming we solve those areas, yeah, I think we're really on our way, and there are enough commercial drivers to this thing that if we build it and it doesn't work, we still make money. If we don't build it, it makes money. If we build it and it works, it makes a lot of money. So, I mean, that's really how I'm approaching this thing. And when Edwards first came to me, I was pretty skeptical, but over 2 years, I've really looked at this thing in a lot of ways. I have to be a true believer. I'm up here. I mean, if I was saying it can't be done, then why would you guys listen? But, I think I'm pretty realistic in what's happening. So I think it can be done. Yeah. In the back? That goes back to the electricity question, and we don't think we have a good answer for that. One guy says yes, one guy says no, and we're not going to know. One of the things that we're doing, in the next few weeks, we're going to launch this probably about 500 feet. Part of one of the questions we're trying to answer with this $1 million challenge that's going pretty high is what happens to stag. And what we make the ribbon out of is probably the biggest factor. And since we don't have a ribbon, we can't even start that testing. So not much of an answer there.
What are your maintenance when you have, for example, something? I mean, are you going to need robotics?
Well, maintenance is a really big question. Give me an narrow.
I was thinking, if something was going there, and maybe you got something like that, and then just a release.
Back to the design, and some of you guys probably can't see this, but one of the things we did was make this modular. So there's one piece, there's two pieces, there's three, and there's four. The idea being that we can take this off and separate the two tread systems away from the ribbon. So let's say something bad happens. Insert a random failure, whatever it is. You've got one ribbon up, or you've got one that's stuck on the ribbon. You've got the one below it that's got enough power to come up, either do one of two things. Push this one, so it's a tow truck, instead of a tow truck, it's a push truck, or release it. You lose the release the halves, it falls, you lose the payload, so, that's a factor, but you can just knock it off the ribbon. It's more important to keep, barring that there's no people on that payload, it's more important to keep the ribbon in place than it is to, and so we've got, probably people, in case anybody is curious, we're looking to launch this thing April 12th, 2018, and we feel that people will probably be a regular cargo within probably 2 years after that. Because one thing that's great about this, the construction process is we have already sent up 270 construction lifters. We know how to do this. There is no rocket system that has had 270 launches. By the time we finish construction, we're better than any rocket system. We're safer, we're more reliable, we're more tested. So we think people are going to be up there pretty quickly on. And so, but that's, we've got to be able to get things off there.
Things go wrong with that, you don't want to take the rocket to fix that.
Well, we'll assume we're going to have people up there, but there will be robotic. Yeah. Hang on just 1 second. Okay, technically my time is up. I love this project. I can talk for hours. So if you want to leave, you can. If you want to stay, you're welcome to. Okay? Yes?
Sorry, two quick questions. First is, are you going to sell stock?
Yeah. I'm not.